Alright, so in this video we will talk about torsion, which is last of a bit left from the previous discussion. To review what we have so far, consider this three space, right? So we have our XYZ axis and we have this red curve, which is the space curve that we are interested in, and there's a point P here. So what do we have so far in terms of our result is that we defined this t vector, which is your tangent vector, and that tangent vector can be found using, it's the unit vector in the direction of the derivative of the position vector. Now, using this tangent vector, we were able to define something called the curvature given by kappa, which is dt over ds. It also had other forms such as t prime over r prime. So it's the ratio of the change in the tangent to the change in position. And then you had the second form, which is your cross product with the second derivative form. And pictorially, if you look at it, what this gives us is, it gives us how this curve is moving along this plane. So imagine this particular plane here that contains the tangent line, and that's where the space curve is living. And the space curve, it's curving in a perpendicular direction to the tangent, and that's what gives us the curvature. Then using the tangent, we define the normal vector, and the normal vector is simply the rate of change. It's the unit vector in the direction of rate of change of the tangent, and this normal vector points inward in this way as shown here with n, and is normal to the tangent. And then lastly, we defined a binormal vector, which is given by taking a cross product of the tangent vector and the normal vector, and this will point above here at 90 degrees with both the normal and the tangent vector, by definition of it being a cross product, so it's perpendicular. And this b also forms a plane with the normal vector, right? And if you look at the quantity dB over ds, which is how does this binormal vector change over the position on the curve, then that gives us this other direction, which is parallel to n. So they form a plane. And this quantity or this expression dB over ds is what we are going to use to define torsion. Okay, so what this torsion is it's kind of like curvature, but in a different plane, right? So when you think of curvature, it's in the plane of the space curve, whereas when you think of torsion, intuitively it's a measure of how much the curve twists. Okay, and what we mean by how much the curve twists is it's kind of like curvature but in a different dimension. So for example, if I look at a circle, right, intuitively this circle has some curvature, which we saw as constant, and it has curvature in the sense that at different points it kind of turns. But we would say that it doesn't have any torsion because there is no twisting happening. So here it has a non-zero curvature, but it doesn't have any torsion, or because there's no twisting involved. And what I mean by twisting is, now instead of the circle, if I cut this circle and I open it up and then I stretch it out and I make it a helix, right? Now this has a curvature because along the curve it is turning, but it's also twisting. So it also has a measure of torsion. So that's the basic difference between curvature and torsion. Curvature happens on that plane in the direction of the space curve. The twisting or the torsion happens in a plane that is normal. It kind of lifts out or twists out. And in order to define this quantity, what we observe is that dB over ds, that's the change in binormal vector, is parallel to the normal vector n. Okay, that's because they form this plane over here. Now whenever vectors are parallel, they are just scalar multiples of each other. So we can write dB over ds equals some negative, where this is tau, negative tau times n, because these are parallel. The negative sign is just because it's for a directional thing that's used in physics. It doesn't matter. Well, it matters in the sense that it is the convention, but that's just because we're choosing tau positive to meaning twist out and tau negative to mean twist in the opposite direction. So now if we take the dot product on both sides, what you get is dB over ds dot n equals negative tau n dot n. But n dot n is just 1. Is 1. Why? Well, it's because it's a unit vector. So we get this equation, which is tau is negative dB over ds dot the n vector, and this is defined as the torsion. This is the torsion of a curve. Now, just as we did with curvature, we had a dt over ds definition, but that was not entirely very readily applicable. So we have a better result, or a more easily applicable result. And we'll use the same sort of, this is a similar derivation of stuff to curvature. That is, we will start with chain rule. So dB over dt can be written as dB over ds and ds over dt, so that dB over ds, that's what we're interested in, is dB over dt divided by ds over dt. dB over dt is simply b prime, right? It's the derivative of the binormal vector, and ds over dt we know from previous work is absolute value, or is the magnitude of the r prime vector. So plugging this in, what do we get for curvature? Tau at t is dB over ds, negative dB over ds. So it's a negative b prime t over r prime dot with the normal vector. So if I take b prime and I dot it with the normal vector divided by this magnitude, this gives me another definition for torsion. So this is torsion. Let's look at an example. Once again, since we had the helix, so let's find the helix torsion. Right? So helix is given by cosine t, sine t, and t. So you have the sort of recipe here. You know all the things that you need, right? Which means you need b, you need n. And remember, to find b, you also need t. So let's do all of that work. Since we've done this before, we know r prime is negative sine, cosine, and 1, and thus we know that the magnitude of this comes out to root 2. So we've done this before. And if you look at the example from the previous lecture, for the helix, we also computed the normal vector and the binormal vector. The normal vector is negative cosine t, negative sine t 0, and the binormal vector has a 1 over root 2, and it is sine t, negative cosine t, and 1. So plugging all of these ingredients into the formula, the recipe up there, Well, I suppose we need b prime t. So let's find the derivative of this. 1 over root 2 is just constant. Cosine t. Negative cosine t will give me a sine t. And 1 will just give me a 0. So what do I have here? I have 1 over root 2 cosine t sine t 0 dotted with negative cosine t negative sine t 0, which is n cap, divided by magnitude of our prime vector, which is root 2. So this is 1/2. Dot product is a scalar quantity, so it's going to go component wise. So I get negative cosine squared negative sine squared. And remember, the formula also has a negative here, which I'm missing. So this becomes negative half, negative 1, which is 1/2. So the torsion helix has a torsion of 1/2, which is a constant torsion for this particular helix. And if you look at how the space curve of this thing, the sort of the twisting is constant. The twisting doesn't vary, and that's why the torsion doesn't come out to be a function of a position or parameter t, but a constant like half. Which raises the question, what if, is that always the case? And obviously that's not the case, just as we saw with the circle, right? The circle had a curvature constant, but if you, that's not necessarily always true. If you change the shape, if you take another, for example, the example that we saw in the lecture had a different curvature at different point. Similarly, for torsion or for twist, the helix is the basic structure, so it has a constant torsion, but that is not always the case. So which brings us to the last result. This is a theorem that I will state without a proof. The work is similar to the theorem for curvature. The torsion, so there's a torsion result of the curve given by vector function r is, it's going to have again a bunch of familiar things. So recall this cross product comes from the curvature, then you dot it with the third derivative of r, and in this case the denominator is a little more daunting. So you have the magnitude of this cross product squared. So given any curve, you can also use this particular formula or recipe to find the torsion. So here you're just using r prime, r double prime, r triple prime, and then cross product of r prime and r double prime. All right, so that's it for discussion on torsion, which leaves us with one last topic, which we will go over in lecture tomorrow, and then whatever remains or is not covered will be posted as videos.